Yes, welcome everyone to GeoHug. So before we kick off today's session, I'd just like to take this time to acknowledge the traditional lands which we're all coming from today. I'm here on the beautiful lands of the Gadigal of the people of the Aurora Nation, and I'd like to pay my respects to the elders past, present and future. So I'm so excited to have John Thompson in the hot seat today. So John has had an extensive career working in universities, resource companies and councils, and more recently in a consulting business called Petroscience Consulting, which is focused on exploration, mining, innovation and sustainability. So I feel so privileged that he has joined us today to chat about exploration and mining, a world of change, where he will share with us 100 years of geology history. So it is going to be a great session. I hope you all enjoy it. Please use the chat. You'll have the chance to jump off mute and we'll open up the floor at the end. And yes, thank you so much, John, for joining. It's just wonderful having you.
And before I kick into it, I'd just like to do the same thing as Jessica did and do a land acknowledgement. I'm located in the traditional, ancestral and unceded territory of the Coast Salish peoples, and that includes the territories of the Musqueam, Squamish and Tsleil-Waututh nations, and that covers a large piece of the west coast where I live in and around Vancouver. So moving along and getting into the talk here, I've started here with the slide, the title, Exploration and Mining, a World of Change. And this is a talk that I put together for the Society of Economic Geologists, SEG 100th anniversary meeting that was held in Whistler in September last year. And so I gave this talk because I was trying to encapsulate the big things that had happened over that 100 years of history that SEG represented, and talk about how it played into kind of what we do, both in terms of exploration and in terms of our science. And so I've more or less taken that talk, and I apologize to those of you, if you were unfortunate enough to have to listen to it already and you want more, that's terrific, but you feel free to drop off at this moment if you think you've heard it all. But I've adapted a little bit, hopefully, for this audience. So we'll get right into it, hopefully. Okay, so the world. This is a very brief view of the world from 1900 to the present, 2022, and it touches on the kind of the biggest things that kind of happened over that 120 year period. And of course, that built on the Industrial Revolution. So we had 200 years of the Industrial Revolution, which changed the world significantly: mechanization, power generation, transportation, electrification, et cetera, cars, all that really came out of that period. And as we came into the 1900s, I have to say I wasn't around at that point, but I'm just sort of trying to capture what was going on. It was all about infrastructure. Everybody was building things. Railroads were still being built. Canals in the UK were being built or had been built largely, but it was about a lot of infrastructure, and that uses resources. And then, of course, we went into the devastating periods of World War I and World War II, massive use of resources and massive change in terms of technology, both in all respects, but particularly in our business, that came out of particularly the Second World War. And that led into a period kind of in the 50s through to the 80s, 90s of what I call big science and technology. So over here, this is what I've labeled big science and technology. And that was kind of the heyday when so much happened around developing new technologies and new ways of doing things, very much on the mechanical side. But as we moved through that period, it became increasingly digital. Computers became a fact of our lives, and that started to have big impacts on the technology scene. And then as we get into the 1990s through to the early 2000s, it was really about the developing world, especially China. China developed us at an unbelievable rate through that 20-year period from 1990 to 2010. And that development created a massive demand for resources. So if you put that all together, you end up with this kind of exponential curve, and many of you will have seen curves like this. This is a curve you could say is for population, human population growing exponentially. You could say it's about energy use and CO2 emissions from energy growing exponentially. You could say it's about resources use and so on. All of these things were happening at that time and following this kind of curve. And in case you think I'm just making it up, here's some facts and figures. I'm not going to go through these in any detail. These happen to be mainly from our world in data. Population down here, bottom left. This goes out to 2100, and the view of many people is that we will start to flatten off population growth over the next 40, 50, 60 years. And hopefully that's the case, although declining population will have some interesting ramifications as well. But along with population growth, exponential growth in energy use, energy consumption on the bottom right-hand side over that 100-year period. And of course, the two are linked very closely together. And because energy produces CO2, most of it, all fossil fuel production produces CO2, inevitably there's a direct correlation between energy consumption use and CO2 emissions. And of course, in our business, we saw the same thing in terms of metals, particularly the major metals, iron, copper, zinc, etc., also have gone through this period of exponential growth, almost exactly mirroring energy and CO2. So that's the world we've lived in. We've lived in an exponential world. And of course, the immediate thought you have, if you're a person who doesn't know anything about our business and you see a graph like this, you think, well, how can this go on? I mean, we can't just go on being exponential forever. And if we look at our resources, surely if we've got exponential growth like that, we're increasing year on year, we're just going to run out. And of course, many people have said that, exactly that we're going to run out. And the truth is that that's not going to happen. And I'll come to that in a moment. So if we just look at the mining now over that same kind of 120-year period, back in 1900 was when we first developed bulk mining. The first open pits came around 1900. The Bingham Canyon pit was the first serious large hole in the ground. It's now an awful lot larger than it was back in 1900, but it was the first attempt really to apply economies of scale in order to extract minerals. Around the 1920s, plus or minus, we had the development of flotation, game-changing. It was allowed us to recover sulfide minerals from rocks and therefore the metals within those sulfide minerals. Interesting fact, Cam would love this. An interesting fact is that 3 countries claim responsibility for flotation. Australia, of course, and I'll put Australia first since I'm probably talking to a dominantly Australian audience, but Canada claims it too, haha! And I obviously live in Canada, so it's probably Canada that did it. Meanwhile, the UK was still in the business of resources back at that time, and they claimed flotation as well. So it all happened about the same time for different reasons, and there's lots of anecdotal stories about who got there first, but the result was still game-changing. And then as we get into the Second World War, the post-Second World War period, there was an incredible amount of technology that was developed during the Second World War that then came out into the mining business. So probably the most important would be hydrometallurgy, the relation to leaching and particularly solvent extraction. And that allowed us to leach metals from rocks, for example, copper, eventually gold, uranium, and recover them very, very efficiently. At the same time, we going from open pits, we started pushing into deeper mines but mining them at considerable scale. So not just chasing narrow veins, which people have done for hundreds of years, but actually started to mine that bulk in the underground world and so on. So there was a lot of big change that happened. And then as we get into the latter part of the 20th century, communication came along, GPS, GIS, we started to have the digital world, the computer world started to impact our business, allowed us to do much more sophisticated planning. And at the same time, we started incorporating new physical ways of doing things, mobile crushing in pits, for example, different ways of actually doing what we do in terms of moving large amounts of rock around. And finally now, into the last 20 years, it's all about the digital mine. It's about sensors everywhere. There's sensors on everything in mines. Unfortunately, we probably only use 10% of the data, but at least we're sensing it. And on top of that, of course, that once we can sense and do things with sensing, we can automate. And so automation is a big deal. And the net result of all that, again, is this exponential curve of growth for production. And of course, unfortunately, with production comes waste. And here's just popping in here on this slide here is a diagram that Anita Papakor-Fox used in this GeoHug forum to talk about the exponential growth of waste as a result of exponential growth of mining. And of course, the opportunity there is to do something different with that waste, to reduce it or to reuse it in some way that will give us a better reputation. So these things are all just the facts of life, and it is through this that we met the rapidly increasing demand. But back to the point I made previously, if it's increasing at this rate exponentially, surely we're going to run out. Doesn't that make sense? Well, no, it's not the case. In fact, if you look at the graph at the bottom right there, the green line is increasing production from 1994 to 2018, so a 30-year plus or 25-year, 30-year period. Steady growth, around 2 to 3% growth each year in terms of copper production. But if you look at the black line is reserves, and lo and behold, the reserves have increased year on year. At the same time as we've been increasing production, we've been increasing reserves. And many of you will know why this is the case. It's because we've done a great job of turning resources into reserves, the part that's economically mineable. It's because we've been able to expand our mines. And why have we been able to expand our mines? Because as the price has gone up, we've dropped the grade, the cutoff grade, and therefore the mines can get bigger at lower grade. Now, the downside of that is the waste. When we start moving more and more rock for less and less metal, we produce more and more waste. So there's a downside to that, but this is the story of how we've managed to maintain our production and can continue to expand the reserves. New technology has played a role because new technology has lowered our costs and again allowed us to mine at lower grade and therefore expand our mines. And yes, there have been very significant new discoveries. Sometimes new discoveries get a bad rap. People say we're not discovering enough, and that may be the case, but time has told us that we actually seem to always produce enough. So we meet this ongoing exponential growth of production, and we do it by making discoveries. So I'm not a person to knock discoveries. I think it's very hard to find and to accurately capture all the discoveries that are being made because many don't see the light of day in major companies until long after they were first discovered. So they come into the picture as a mine expansion when in their day they were a major discovery. So that's fine, but of course the question is, can we keep doing this? And that was the point I made previously, particularly with the new demand for clean energy, the energy transition and so on, and projections for even greater growth in our mining space for commodities like copper and nickel and so on. Can we actually maintain the graph on the right going forward? And that's a conversation for a different day and not the purpose of my talk today. So I'll leave that thought with you and we can come back to that if you want with the discussion. Let's go down to exploration, which is the main point of my talk here, and look at the same 120-year period. And what I've done here is I divided it into three kind of slots. The first one is the era of field observations. The second is science, and particularly plate tectonics. And the third is data science. So if you look at the bottom now, you can see the things that I've sort of talked about here. Back in the 1900s, geologists were prospectors, really. They had amazing skills, but they really were prospectors, very sophisticated, very clever prospectors who recognized things like alteration and had sort of models in their own heads, but very much in the way that a prospector does. By the early 1900s, geologists were becoming quite sophisticated. They were starting to make observations of combined technology. They were doing geochemistry. They were even doing biogeochemistry. Biogeochemistry started being used around 1920, people sampling trees and bushes to see if they could detect metals. At the same time, those geologists really were engineers as well. Many geologists were engineers and vice versa. So the gap that we sometimes talk about when we denigrate engineers as geoscientists or vice versa if you're engineers, that didn't exist back in the early 1900s. They were one and the same thing, and geologists developed mines. They built mines. So they were a lot smarter and more capable back then than we are now, obviously. And then we get into the period of the Second World War, and the main technology that came out of the Second World War for our business was geophysics. Geophysics was used during the war, or the physical measurement of moving materials to detect submarines. So many techniques, magnetics, electromagnetics, etc., were invented in the hunt for submarines in the Second World War and then were adapted to exploration in the 50s and 60s. At the same time, geochemistry started to be used much more widely. Analytical tools started to become available more routinely, and so people started doing regional geochemistry. For the first time in the 50s, people covered large areas. In the late 50s through to the late 60s, most of British Columbia, the province where I live, was covered by regional geochemistry by one company. And that company was Bear Creek Mining, which was an affiliate of Kennecott, now Rio Tinto. And they covered most of the province and arguably discovered many of the deposits, even though they didn't take them forward or drill them out or even discover them. So that's a remarkable period of time. Post-war then, big science, it's about thermodynamics. The underpinning of our business comes from thermodynamics. You may not like to hear that, but it is a fact, and I'll talk a little bit more about it in a moment. But along with that came technologies that allowed us to look at little bubbles in quartz, fluid inclusions, to measure isotopes and to start to incorporate those data into models. And by the end of that period, the 80s through to the end of the 20th century, we really started to develop sophisticated deposit models, and I'll talk a bit about that. And we tested them, for example, by using the age of the things we were looking at to see if they fit the model that we were talking about. So the role of geochronology became enormous and associated analytical tools that just got better and better. And now finally, last piece, we're in the digital world. We're in the software, we're in data analysis, data science. We're starting to become much more sophisticated about the models that we use. And the net result of that is the world we live in now is a world of data. a world of reserves. We're creating reserves. We're converting resources to reserves. And yes, we're making new discoveries through a combination of different approaches. So I'll give you a few quick examples of some of these pieces of the puzzle, if you like. So the first one is that this experimental analytical research from 1950 to 1980. This is the thermodynamic era. This is when people did experiments to try and understand the alteration minerals that we see in the rocks, or to understand the sulfide minerals that we see in sulfide deposits. The one on the right is for nickel sulfides. This work sounds dry for some people, for many people perhaps. It's not their favorite piece of geoscience, yet it is the underpinning of pretty much everything we do and understand in terms of ore deposit models. It led then, particularly on the hydrothermal side, into three amazing volumes shown here in 1967, 1979, and 1997, called The Geochemistry of Hydrothermal Ore Deposits. And if you haven't looked at these, you should. They're not only, they're amazing at their time, but they still have a lot of very important information in them. And that kind of work led to the diagram that I show on the left. This is a combination of different people's work, but it shows the stability of some critical minerals that we found in and around porphyry deposits, particularly at the high temperatures up in this part of the diagram here. And then down here in the epithermal environment at much lower temperatures. And depending on the trajectory you take through this diagram, the timing and the conditions that the system has gone through, you will develop these minerals and you will develop zonations using these minerals, which we now understand and we use for mineral exploration. So fundamental science, fundamental thermodynamics, which we inherently use all the time, even if we don't look at this diagram anymore, we still know that we're moving up temperature if we go, for example, from white muscovite or white mica into a biotite, to a rock with secondary biotite alteration and Cape Elspeth. We have a sense of that. We have a sense also of the pH. Are we looking at kaolinite and iodinite, or are we looking at mixed layer clays, intermediate argillic alteration? So this is our underpinning, and it's really important that we don't forget that. And it's great that we talk about thermodynamics and that piece of science, but the biggest thing that happened, of course, wasn't that. The biggest thing that really happened in that period from the 60s through to the 70s, 80s, was the plate tectonic revolution. And that changed the way all geoscientists looked at the Earth and the way we looked at mineral deposits. So if you haven't read it, there's a book here called Plate Tectonics, An Insider's History of the Modern Theory of the Earth by Naomi Oreskes. It's a fantastic book, number of different papers by different people to talk about the whole history of the plate tectonic revolution. But remarkably, literally within years of this becoming the accepted paradigm, we already had a book on mineral deposits and plate tectonics by Sam Sawkins in 1972. And Dick Silto, who's been writing papers almost forever, I think, I wrote one of his early papers about mineral deposits and plate tectonics at the same time. So we were already at that point starting to convert our thinking to a new scale of observation, a new scale of understanding, a global scale in terms of plate tectonics. We were starting to think about the role of island arcs, or in this case, continental arcs, the Cascades in Washington state, famous for the town of Vancouver, of course. And this is you can see the arc volcanoes running up to here, and that's on the ring of fire, the west coast of North America. And then equally important, we have the spreading ridges and the terrific amount of work that's gone into understanding their roles. So this changed everything. The plate tectonic revolution changed the way we do mineral exploration to a significant degree, and at least the way we thought about different deposits in different environments. It was, I would argue, the beginning of mineral systems approach to exploration. So here's some examples of some more recent work. This is Jeremy Richards' stuff. Jeremy Richards, in this case, was compiled the Tethyan arc and placed mineral deposits of a variety of different styles into the various events that happened during that Tethyan arc developments, many arcs, and then collision and so on, and then capture of these various elements that make up the modern tethys. Over on the right, again from Jeremy Richards, is a view of subduction zones, in this case porphyry deposits, showing that it isn't just convergent processes and subduction that leads to porphyry deposits, a wide variety of collisional events, post-collisional events, and so on that allow porphyry deposits to form. Much more complexity than we realized at the outset, and part of our increasing understanding of the role of plate tectonics in the world of mineral exploration. And it's not just about arcs, of course. Some of us love to spend our time on arc volcanoes and imagining porphyry deposits at depth. but it's also about rifts. And one of the major rifts that we see in North America is the Mid-Continent Rift that runs up through the Great Lakes, through Lake Superior, and then heads down to the south-southwest or west-southwest, down into the central part of the United States. And associated with that, we have major nickel deposits, nickel-copper deposits, and stratiform copper deposits as this rift started to develop as a sedimentary basin and then largely failed. And of course, it's not just in the continents that we see rifts on the ocean floor and actually within arcs. Over here, the picture on the right, this is the Lau Basin coming down through the Tonga-Kermadec Arc, which is rifted. And within that rifted arc, we have an abundance of hydrothermal vent sites that have been well documented by people like Cornell, Durand, and others. So rifting is a critical process, but it's related directly to the formation of a variety of different types of ore deposits, just as arcs and arc magnetism is also related to different styles of ore deposits. And that is built into our thinking when we think about the deposits that we're going to look for and where we're going to look for them. And that led to ore deposit models. Ore deposit models started post-plate tectonic revolution to become far more significant. As I said, they started to get into thinking about systems and larger scale processes rather than just looking at the deposit themselves. But the deposits themselves still went through big changes in terms of the models that were used to understand them and used in exploration. And then probably the biggest change was with volcanogenic massive sulfides or volcanic hosted massive sulfides if you're in Australia, the deposits that form on the seafloor or perhaps just beneath the seafloor. This early work happened really, people started in the 50s and 60s, recognizing that there was an asymmetry around some of these lenses of copper zinc sulfide mineralization, and the minerals on the one side of them were different than the minerals on the other side. So this asymmetric pattern either side of the sulfide, and very clever people like Richard Stanton from Australia, from the University of New England, thought that perhaps these had formed syngenetically on the seafloor. That was pretty radical back in the 50s, but it's an idea that grew and steadily became more and more popular through the 60s and 70s. And then, of course, at the end of the 70s, we discovered sulfides and black smokers and sulfide accumulations on the seafloor, and that changed everything. We now had the modern analog for VMS formation, and we could use our understanding, the developing understanding of the seafloor, now to explore for these deposits on land. So this was breakthrough stuff, late 70s and through into the 80s, and of course there's been many discoveries of hydrothermal vent sites since then. From an exploration perspective, this new understanding meant that we had to understand volcanic stratigraphy. We couldn't just use some fictitious structure to slam the sulfides through. We had to understand the volcanic stratigraphy to know where the deposits were likely to occur. We also had to understand the petrology of the volcanic rocks. Some volcanic rocks seem to have associations with different suites of metals. We had to understand hydrothermal alteration. This was also the EM era. This is when electromagnetic surveys, particularly airborne surveys, first came to be a commonly used technology through the 60s and 70s, led to many discoveries which turned out not to be discoveries, of course, many false anomalies, but many significant discoveries, Eskay Creek being the most important one in 1963. And not to be outdone, gravity was also being used, and it was gravity that led to the discovery of Neves Corvo in Portugal in 1977. So geophysics, the use of geophysics really played strongly into the discovery of volcanogenic massive sulfides or VHMS deposits, as did the recognition of the model, the environment in which they formed. This is a cute little cartoon from a small deposit in northwestern British Columbia, which was found in 1989, and it's the Eskay Creek deposit. Eskay Creek is quite small. It's only mined about 2.3 million tons, but produced a phenomenal amount of gold and silver. So you can look at the amount of gold and silver there that came out of that 2.3 million tons. So it was running around 60 grams of gold and a couple of thousand grams of silver per ton. So very significant deposit formed on the seafloor, well documented by the work of Tina Roth and others who studied this deposit and showed these plastic beds of sulfides and sulfur salts, which you can see in this picture here, which came presumably from the breakdown of black smokers like this. We also had some barite-rich mineralization that may well have come from white smokers. So a graphic example of a seafloor process. And what's really interesting about Eskay Creek is it really demonstrated that we could get significant precious metal accumulation in syngenetic seafloor processes. And that led to a lot of work in a lot of other places. Porphyry model. The porphyry model was developed through the 1970s, by three very significant papers: Lowell and Gilbert in 1970, Sillitoe in 1973, and Gustafson Hunt in 1975. They put the understanding of porphyry deposits, and particularly the zonation that we get around porphyry deposits, in a way that people could then use from an exploration perspective. This, if you like, again, started to produce a system scale understanding where you could be several kilometers away from the deposit and find a way to vector and organize your thinking, if you like, in towards what was the core deposit. The diagram on the right is of one that's shown in virtually every conference I go to and has been for the last 22 years since it first came out. A de Soto diagram which encapsulates many features of many porphyry deposits on one sort of simplistic diagram, but a very effective diagram that looks at the relationships between different types of deposits from the deep core of the deposit up into the upper parts, which may look something like this, the crater at White Island. So this gave us a whole new understanding of porphyry deposits in terms of the processes and the nature in which they formed. Not to be outdone, the epithermal models, of course, advanced significantly through this time. In fact, the work on epithermal models resulted a lot from geothermal work in geothermal systems from as early as 1900 through to 1960. It included people like Waldemar Lindgren and White, who wrote classic papers about various hot spring occurrences, which gave us the context for understanding alteration. And that eventually led to our understanding of the model depicted in this cartoon from Jeff Hedenquist, which was in part based on an earlier diagram by a guy called Dennis Buchanan. And this placed the context of the system again, the geothermal system, and how it might then form epithermal gold-silver deposits. And Jeff, of course, spent his time working in New Zealand in places like Waitapu here, where we could see some of the processes again in real life, just like the White Island example for porphyries. These active processes in geothermal systems helped us understand epithermal deposits. And of course, black smokers on the seafloor helped us understand VMS deposits. So the use of active and modern analogs became very much part of our thinking through this period. That, of course, is not the case if we go to magmatic sulfides. This is the last example I'm going to draw your attention to. And of course, it's a very important example in Australia, because not only did Australia have significant nickel sulfide deposits, Kambalda diagram map shown on the right-hand side of this slide, it also was the place where really arguably komatiites were truly recognized for what they are. The initial work on komatiites came out of South Africa by the Viljoen brothers, but the detailed work in which it was used particularly in terms of mineral exploration, came from Western Australia and a little bit from Eastern Canada. And so we understand now the nature of these rocks, the spinifex textures rocks that I showed down here in the bottom part of this diagram, and how they can help us understand the volcanic architecture of komatiite flow-dominated volcanism. So volcanology played a role, and we started thinking about things like thermochemical erosion, how these incredibly hot 1600 degrees centigrade lavas would melt their way through the rocks, could extract sulfur and sulfides from other rocks in order to get to a sulfide saturation and form nickel sulfide deposits. So lots of great work by many people, including the CSIRO group with Steve Barnes, but his supervisor, Tony Nordrett, who is also my supervisor, had an enormous role to play in this development of the understanding of nickel sulfide deposits. Arguably, I tell people that it is the most quantitative model we have for a mineral deposit, partly because we can see all the pieces of the puzzle and we can model them quite effectively to try and understand what's going on. Others might, of course, and are very welcome to disagree with me. Okay, so that was the model story, and the models themselves were really helped significantly by huge analytical advances. So this is just some fancy gear in a lot of universities around the world that do a variety of things, from dating rocks better, dating minerals, particularly looking at minerals like zircon, analyzing the chemistry of these minerals and their oxidation state to tell us things about fertility, isotopic work in general, isotopic work on waters, isotopic work on fluid inclusions, just a huge amount of work that's come out of labs like this with a vast amount of data, which has been incorporated into the modern model and modern understanding of a variety of mineral deposits. This is incredible stuff. I do sometimes worry about the amount of data we produce and our ability to actually effectively interpret and incorporate it. And that's where I think data science will come in the future to help us provide a more effective synthesis of some aspects of ore deposit models. Meanwhile, out in the field, the data revolution happened in the field. Suddenly we were collecting data all over the place by the 2000s, early 2000s and on to the present time, whether we were flying drones or using tablets or handheld devices to detect minerals, to detect chemistry, just an amazing amount of new technology that meant we collected a lot more data a lot more quickly. So these are some of the things that I think of when I think of breakthrough technologies in our space, but there's one that not many people talk about, and I just have to throw this in for a little bit of fun just to wake you all up, is the piece of technology that made the biggest difference to my life personally was this. This is a plastic water bottle, and it meant that all over the world I was able to drink clean water and not get sick. And so that was a breakthrough technology for mineral exploration. Now, of course, there's a downside to plastic bottles. It's not all good by any means, but in terms of health, it had a hugely beneficial effect on probably all exploration camps worldwide. Having spent a number of years in jungle camps, particularly in places like Indonesia, being decidedly uncomfortably unwell, being able to have clean water in every place I worked was an enormous change. So that takes us into data. So the 2000s, it's increasingly about data, how well we use data, and how effectively we can take that data and use it as part of our model and part of our exploration approach. So this is one of my favorite examples. This is work by Eldorado Gold from the Kışladağ deposit in Turkey, which is a porphyry gold deposit, really interesting deposit. And I use it not to claim that this is the best thing in the world, but it's a very practical example to me of how data was very effectively used. So what they did was they did spectral analysis. They used a handheld spectral device. So this was really largely pre the advent of core scanning technologies, although in part it overlapped that. And it was a choice in this case by the Eldorado people to keep doing the technique that they'd already established. They collected all the spectral data, and then this data was treated by Ozspec, Sasha Pontool, in particular, who took the shortwave infrared data and then used a machine learning approach to convert that into spectral response. And so that's shown here. I should just point out the scale here. The scale of that diagram here, you can see the 200-meter scale bar here. So it's about 1,200 meters by 800 meters. So these are numerous drill holes. These are thousands upon thousands of measurements. So that's the important thing to remember. And out of that comes these diagrams that show the spectral response, spectral response for white mica, kaolinite, tourmaline, water break, alunite and tourmaline there, and they're depicted in some of these rocks here. Incredible piece of work. And this Osiris artificial intelligence spectral infrared interpretation system that led to being able to do that. And it's, as I say, pretty much a machine learning type technology. This is the kind of thing we can do. And it's not only important, obviously, for mineral exploration, because it starts to depict the zoning between these minerals. You can immediately, visually, in these two-dimensional depictions of 3D data, you can see variations of where the tourmaline is versus where the white mica is. So you can get some kind of zonal relationship in your head. You can see where alunite is versus where kaolinite is. So that you immediately can start to use that from a mineral exploration or a targeting perspective. But these data are also really important from a geometallurgical basis as well, because some of these minerals, particularly the presence of kaolinite, can have an adverse effect on the heap leach process at the Kışladağ mine. So being able to quantify the amount of kaolinite throughout their deposit allows them to plan and stage their heap leach development much more effectively. Okay, so I'm just getting to the closing stages here. I want to talk a little bit about models and bias. So I talked about models and development of models, and there's no question that we are a model-driven discipline, model-driven science, and of course, in the context of exploration. And the problem with models is while they are wonderful ways of depicting what we think has gone on in the earth to create concentrations of metals, they are very often influenced by our own personal biases, cognitive bias, without any question. And this can be in the form of anchoring, because we love to use key examples to hang everything off. It can be because we're ridiculously optimistic as members of the exploration community, or because we seek the data that proves the point that we think we're right. And we all do this. This is not some failing of economic geologists. These are human facts of life that we all have biases and we all have to operate within them. we can't deny them, but what's really important is that we understand them and work around them so that we're not governed by them. A really good example of where this played out is the debate around Archean gold deposits, orogenic gold, if you like, shear-hosted gold, that went through a period in the sort of early to mid-70s where virtually every deposit went from being a structurally controlled or shear zone controlled deposit to being an exhalite that formed on the seafloor. So this was the heyday of the VMS movement. So everybody was totally enamored. They loved VMS deposits. They loved this new model. So suddenly everything was formed by it. It was an absolutely classic case of huge amount of bias. Over a period of time, then that rolled back and the structural geologists got into the fray and they clearly pointed out that no, these things were structurally controlled. And we went back to developing the orogenic gold model. But even then, that wasn't quite the end of the story because this famous deposit in Western Ontario in Canada, the Hemlo deposit, didn't fit either of those models really. It was enigmatic. It wasn't clear what it was, but it was clearly early and therefore was not a structural overprint on pre-existing rocks. The true origin of Hemlo remains to be determined. But the work on Hemlo then came to a re-examination of the Bousquet de Montgomery-Laurent camp by Benoit Dubé and other people, and the realization that these actually were VMS deposits, albeit very gold-rich, just as in the context of Eskay Creek being very gold-rich. So we've gone through this incredible cycle over a sort of 30, 40-year period of orogenic gold or structurally controlled gold to VMS to back to orogenic, and then suddenly realizing, well, actually some of it was VMS after all. And could we have got there quicker if we hadn't been governed by our bias? I think unquestionably we could have done a better job of going through this period if we'd been a little less biased in our interpretation. The bias becomes really obvious when we make a new discovery. And that's called recency, recency bias. It's when we get really our mind gets set on something new and fantastic that's just happened. So we discover Olympic Dam, we discover Eskay Creek, and we all want to go looking for Olympic Dams and Eskay Creeks. In Nevada, people got really enamored with the epithermal model and the geothermal association or analog, and suddenly everything had to have a center, or everything had to have a volcanic dome, or everything had to be a diatreme. In fact, these phenomena are just symptoms of the system that contains epithermal deposits. They are not the reason for epithermal deposits. They're part of the overall volcanic and landform setting. So again, too much bias that drove our desperation to have a panacea or something that would explain everything easily and allow us to raise lots of money to do exploration. And it's only really now, I think, that we're starting to develop a much better way, a much more quantitative way of looking at our models so that we're not so governed by those biases. And lastly, I'll leave you with the new techniques. Well, I don't need to say much. Selective leach, all of us have probably played with selective leach, have gone through cycles of believing and disbelieving, and hopefully will reach some kind of rational level of how and when we use it. And EM, of course, was done to death in some places where people have flown with better and better technology, only to generate more and more targets at greater and greater depth, most of which, of course, were false anomalies. And, of course, we don't know everything. And our realization that we don't is a very important part of our understanding. Olympic Dam has been studied immensely by fantastic people, Kathy Ehrig among them, and we have a tremendous understanding of the deposit in terms of its mineralogy, its physical character, its chemical character, the nature of the rocks, even the origin of the rocks to a large extent. But we truly do not understand the origin of Olympic Dam, and let alone the origin of the deposits which may arguably be part of the same family, the IOCG suite of deposits. We have a very poor model that truly explains these deposits. Although we can describe them well, we can't really understand them. And the Witwatersrand in South Africa has produced probably 50% of the world's gold or more over time and has a significant amount remaining in it. And yet it's been hotly debated as to how that happened. In fact, that debate at one conference almost came to blows when the two protagonists were so vehement in their belief that they had the answer that they could no longer tolerate the other person talking. And again, now we're beginning to move to a better understanding of this because we've finally woken up to the fact that the environment at that time, 3 billion years ago, was very different than it is now. And so the pH of the waters that flowed over the land surface were very different and probably contained a lot higher quantities of metals than the equivalent ones would do now. Sediment-hosted gold, getting tremendous debates in Nevada about their origin. And finally, a big unknown is we really have a hard time telling the difference between metamorphosed deposits and deposits that form under metamorphic conditions. And so Carrington, Broken Hill are examples, and the pictures I show here are from the Curaçao Valley in Brazil that almost certainly formed under high PT conditions. So we have a lot to learn. We need to still be a little humble when we think about our role as economic geologists. So that may be a little bit of an unsavory note, so I don't want to finish on that. I want to finish with something much more positive. I want to point out that we may not have always got it right as economic geologists, but we actually contributed to a lot of geoscience. Geoscience in all its forms has helped us, but we have helped geoscience too through economic geology. And these are just some examples where we've contributed to major understanding of Earth problems or Earth development of our planet. The Earth's atmosphere is a great example. Metals have very distinct geochemical characteristics. They respond to oxidation state. And so the nature of deposits and the preservation of deposits through time tells us about the atmosphere. The origin of life. Hot smoke, black smokers are an indication of processes that might have played a role in the origin of life. In the oceans themselves, we understand ocean circulation and ocean chemistry in part because we understand black smoker seafloor type processes. And therefore, that helps us understand broad-scale geochemical cycles. We're now beginning to understand the role of extremophiles, unusual little microorganisms and bacteria that can live in unusual places, like next to black smokers, and the role that they play. So that's playing into helping geomicrobiology. And then, of course, the big one, like plate tectonics, we've been governed by plate tectonics, but we have contributed immensely to it by looking at the deposits. And the BC, the British Columbia alkaline porphyry deposits are a very good example because they tell a story about two terrains that must have been joined because they formed these very unusual deposits at exactly the same time. Although for many years, people tried to slam a chunk of ocean crust between them. And lastly, of course, the work that I touched on in terms of geothermal processes, volcanic gases, all of that has had an interplay between economic geology and other parts of our discipline and science. So I'm going to close by posing a question. We've talked about 100 years, very rapidly 100 years of history of economic geology, but what comes next? Is this exponential curve going to continue? What's it going to require? What are the technologies? What are the approaches? What are the ore deposit models that are going to have to be developed to take us on into the future? So I'll leave you with a few thoughts. These are my thoughts, so you can absolutely critique them because I don't own them. They're just my best guess. Nobody knows what's going to happen in the future. So these, if you like, are a few scenarios of things that may be important. Everybody's talking about critical minerals and metals, perhaps possibly too much. I'm always worried that we're just getting a little bit overblown in our perception of their importance, but there's no question they're going to be very significant in the near, at least over the next 10, 20 years through the energy transition. No question that we need to be, as an industry, more responsible in how we make discoveries, how we develop mines and do mining. And economic geologists are going to play a big role in helping that happen. We will need new sources. Are we going to reprocess waste, as Anita would suggest? I hope so. Are we going to do better recycling? I hope so too. But at the same time, we're probably going to need new sources of the metals from the Earth itself. Is that going to be the nodules that are shown on this diagram? Is it going to be from the seafloor? Are we going to go to space? Are we going to use space metals to colonize space? Or are we going to try and bring some of those things back to Earth? That's a bit fanciful, probably a bit far-fetched and a bit out there, but the one that isn't out there is data science. Data science is very real and is going to contribute immensely, I think, to exploration, particularly when it's done synergistically with traditional parts of Earth science and traditional applications of Earth science at the same time. Part of that work is the real-time data, is our ability to actually get data in real time, but most importantly, not only to get it in real time, but to interpret it in real time or very close to real time, such that we can adapt and change our exploration targets and models and drill sites essentially day by day on the fly, instead of finishing one season, going away and coming back a year later to start all over again. We can actually do this process now in real time. And companies like Cobalt Metals is an example of a company that's trying to do that. And lastly, the new science isn't going to stop. We are going to get better and better data from smaller and smaller pieces of minerals. We're going to understand minerals down to the nano scale. There's no question we're going to be able to do that. But the question we have to ask is, how do we convert that knowledge into understanding processes that lead to mineral deposits at the deposit scale, and how does that relate to the macro scale and the big tectonic and petrological features, structural features that we see at the big scale. So there's got to be this big interplay between different scales of observation. The microscience, the technological breakthroughs at that scale cannot simply drive our science. They've got to be built into the way we explore going forward. So with that, I'm going to leave it and hopefully opened up to the odd question, or if people want to rubbish me, that's fine too, because I've said quite a lot and probably more than some people would like. Thanks.